In this question, we're provided with a graph, which is a photoelectron spectrum for a given element. So what that means, you can see on the x-axis we have binding energy, and on the y-axis we have the relative number of electrons. So in the photoelectron spectrometer machine, we have a sample of a pure unknown element. And in that machine, high frequency electromagnetic radiation is shot towards the unknown element, and electrons are removed, and we can measure the binding energy of those electrons. And we can also measure how many electrons have those amounts of binding energy. And based on that, we can figure out the electron configuration. So one thing to notice about this graph is that the binding energy axis is the opposite direction from usual. It starts with the smallest number on the right-hand side at 0.1, and on the left-hand side, it ends up with the biggest number at 1,000. One other thing to notice is that the scale doesn't actually go up linearly like we're used to. It doesn't go 1, 2, 3, 4. It actually goes up multiplying by 10 each time. So those are two things to bear in mind when we're looking at our graph. So to figure out our electron configuration, we need to figure out what do each of these peaks represent. So each peak represents one of our sub-energy levels, such as 1s, 2s, 2p, etc. And the height of those peaks represents how many electrons we have in those subshells. Now, the subshells that are closest to the nucleus, those are the lowest energy ones, such as the 1s and the 2s and the 2p. Those have the highest binding energy because they're closest to the nucleus, so they're most strongly attracted to the nucleus. So these peaks over on the left-hand side are going to represent our lower energy levels, and then as we go to the right-hand side, they're going to represent our higher energy levels. In the question, it tells us this is a complete photoelectron spectrum. So this shows all the energy levels, all the sub-energy levels in our element. So based on that, we know that the one that has the highest binding energy, which is this one here, must be our lowest energy level, which is 1s. So I'm going to label that our 1s energy level. The next one along, this one has the next highest binding energy. That one's going to be our 2s energy level. Our next is going to be our 2p. And finally, we're going to have our 3s. Because based on our little diagram that we've been drawing that looks like this, etc., when we go and we draw our diagonal lines to remember the order, it's 1s first, then 2s, then 2p, then 3s. Okay, so that's what each of our peaks shown here represent. In order to figure out the electron configuration, we need to know how many electrons are in each of those subshells. Now, if we look here at the relative sizes of those peaks, we can see the 1s and 2s peak shown here on the graph are 2 squares tall. The 2p peak is 6 squares tall, and the 3s peak is 1 square tall. We know that 1s and 2s can fit up to 2 electrons, and we know that they're going to become full before we fill the next ones. So based on that, I know the 1s peak must have 2 electrons in it, and therefore I know that this point on the graph must represent 2 electrons. So based on that, I can see 2 squares represent 2 electrons, and therefore on this graph, each square must represent 1 electron. So based on that, I can fill out my electron configuration. In 1s, I've got 2 electrons. 2s, I've got 2 electrons. 2p, I've got 6 electrons. And in the 3s, I have 1 electron. So let's go ahead and fill out our electron configuration now. So we've got 1s2, 2s2, 2p6, 3s1, and that's all. That's everything. So the last ones are going to be empty. Okay, wonderful. So we've got our ground state electron configuration for this unknown element. Let's count up our electrons. So we had 2 in the 1s subshell, 2 in the 2s subshell, 6 in the 2p subshell, and 1 in the 3s subshell. That adds up to 11 electrons in total. The final question asks, which element is a sample made of? So let's have a look. Back at our periodic table, we're looking for something with atomic number 11, since that would have 11 electrons in the neutral atom. And here our sodium atom has atomic number 11, which means 11 protons and therefore 11 electrons in our neutral atom. So we know that this element must be sodium. So this is interesting because a photoelectron spectrometer machine can be used to identify which element we have by performing this technique, getting out a graph that looks very similar to this, and then using that to figure out the electron configuration and therefore which element it is. So this is a method used for identifying different substances.